Hello and welcome to TidyX, episode 50. TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes, and you can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick, and you can find our screencast on Twitter at Tidy_explained. Or you can hit us up, ping us at Gmail, tidy.explained@gmail.com, or go ahead and slap a comment down on the YouTube channel, and we will be sure to get back to you. This is episode number 50, 49 of which have been done under quarantine regulations.
Exactly.
The first one was the only one that we've done in person, and then the next day we were forced to stay in our homes.
And we haven't seen each other in almost a year. So when this episode gets released, it'll be literally the day before 1 year will have elapsed. It'll be 365 days from our first episode.
Yeah,
and
amazing.
I just wanted to take a second to thank everybody for subscribing, for following us on Twitter. It really motivates us to keep on doing this.
Yeah.
I'm having a grand time putting together this content for y'all, and I just appreciate all the kind words that have been shared with us over the last year.
Yeah, definitely.
It's made it fly by.
The shares and the likes on Twitter are really motivating, and it's cool to see people enjoy the content, and then it's cool to kind of see people take the content and say like, hey, I built this dashboard, this shiny dashboard using the ideas from this, and that stuff is really fun to see people take some of the stuff that we try and provide a high level overview of within R, and then take it and blow it out into like something that's unique to whatever is their world or their interests or their data or whatever. So that's pretty cool.
Yeah, so once again, thank you so much for being with us over this last year. It's definitely made it fly by. Can't believe it. We're already at episode 50 and looking forward to doing more. So please let us know if you have any content you'd like us to start working on, or any questions you have. There's no dumb questions. If you're having a problem, I guarantee somebody else is, and we're happy to go through and explain how it works. So, All right. So with that, I think we'll actually get started now that we've been blathering and, being heartfelt for a few minutes. We're now going to get started with episode 50. Patrick, do you want to explain what we're doing today?
Yeah, so today we're going to continue on with some of our work in estimators. We've done the past, 4 or 5 weeks of different types of simulations of performance. And we're going to continue in that same kind of vein this week by building a James Stein Estimator. And this comes from an older paper. It was a paper by Bradley Efron, the statistician, called Stein's Paradox in Statistics from Scientific American. We'll go ahead and we'll put a link up to the paper in the YouTube channel. So if you're interested, you can find it there. But this is a great paper where Bradley uses baseball data to basically show how we can take observed batting averages for players and shrink them towards the group average as a way of accounting for some level of regression to the mean. So in the paper, he does a cool example you can walk through with baseball, where he basically takes like the first 40 games of 17 or so players, and then he tries to estimate the rest of the season of their batting average performance based on those 40 games using this James Stein Estimator. We're going to walk through kind of what it is and how it works, and we're going to build a function, and then we're going to build a cool GT table and visualization, continuing on with our I feel like the last 5 weeks have been all about simulation of performance and GT tables. So we're going to kind of continue down that
Keep
road.
doing that. We're not stepping out quite yet.
Yeah.
So hopefully you've been enjoying it. It seems like y'all have.
Yeah.
So let's get this thing started. So the first thing we do, as always, is load packages. So we've got Tidyverse to do all our data manipulation needs, Lahman to bring in the data that we're going to be using, GT, Patchwork, and Magic for the vizzes later on. First thing we do after we load in our packages is set our theme default to be theme light, so that all our plots will be using the theme light format. I wanted to call out for a second here, if you're pulling a data object from a package and you want to know more about it, so there's a couple ways you can do this. The way I like to do it is do question mark the package name, : the data set that I'm going to be pulling from. So question mark Lahman batting. And that gives us all the information we need to know about this data set here. So it tells us what is X2B, that's the number of doubles hit, X3B, triples, HR home runs. I don't know, some of it's pretty logic, but sometimes column names aren't always super descriptive. And so this allows you to go through and look at what the author was saying should be there. It gives you a nice little high-level view of the number of observations, so 107,000 observations, 22 variables.
I think it's like from season 1890 to 2019 or something. It's
pretty
massively long amount of curate. Yeah, they're 1871 to 2019. So, yeah,
it's
amazing.
Pretty long time running there.
Yeah.
So now we're gonna load it. We're gonna assign it to DF and start going on our merry way. So there we've got the big old data set just saved now into our R session. So what we're going to do first is we're going to subset to keep only the year 2018. In this case, for our simulation, this is what we're caring about first. So we're going to take the DF data set, which is the Lahman batting data set. We're going to filter to keep year ID where the value is 2018. So this will only keep 2018. We're going to select the columns player ID, game, or G, A, B, and H for games, at-bats, and hits. We're going to then group by player because a player could be listed multiple times in that year if they played for multiple teams. We're going to summarize across them. So summarize. So this is now going to return a single row for each group, which is a player ID. Across all the columns, G through H, so games, at-bats, and hits, we're going to use the function sum. So this is going to add all the values together because they're just numeric values that we know should add together. That's what we're going to apply here. So that way we get the single player or the player's total number of games, at-bats, and hits for that season. And then we're going to use the dot groups equals drop. So this is a feature in Summarize in a newish, I think it's been out for almost a year now, version in Summarize, where we can tell Summarize, after this, I'm done grouping. So drop your grouping, and we'll move on with our lives. Otherwise, it can drop one. It can drop none if you want to keep the grouping going forward. So so in this case, we're going to drop it. Then we're going to mutate, and we're going to calculate batting average. In this case, batting average is hits divided by at-bats. But we know there's cases where players didn't actually bat. They just have stats for other stuff recorded. But they just didn't go to at-bat. And so if hits divided by at-bats is an A, we're going to drop 0 because they had a batting average of 0. Otherwise, we're going to actually return the true batting average, the observed batting average that they have for that season. So there we go. So now we have this subset data set with batting average. So player ID, games, at-bats, hits, and batting average for 2018. Patrick, you want to take us through this piece?
All right, so we'll talk a little bit about the James Stein Estimator. There's the link to the paper from the Scientific American article from Bradley Efron. So the first thing I wanted to do here was just get a sense for what sort of sample size maybe in at-bats players kind of had. And so I run a mean, just the average at-bats. Obviously, the mean is going to be a little bit biased there towards players who batted a massive amount. So the quantile gives us a little bit better estimate there. We see the median, which is the 50th percentile, which is now accounting for all the people that actually, in effect, didn't at bat. I also want to look at the what kind of average batting average we had and what kind of standard deviation. So we could see the average batting average is really low because, again, there's a lot of players that have 0 batting average. They haven't batted, or they've batted 4 times and they have no hits. So the and the standard deviation is actually more there than the mean batting average itself. Yeah, so 610 players that had no
0
batting average at all out of
half.
1379.
I don't know.
Yeah,
less than half, but
yeah,
a
so
good chunk,
a large amount. So in order for our James Stein Estimator to kind of go, we want to have a good estimate of a population mean. So my thought here was, what if we looked at the mean and standard deviation batting average of those players that batted at or greater than the median amount, the 50th percentile. So actually, I could have probably done just median player 2018. I don't know why I made that so hard on myself, but
Yeah, it's fun.
Either way, yeah, it does allow you flexibility. You could change that if you wanted to do 75th percentile or 90th. Yeah, exactly. That would be a relatively different result. We'll give you a different result. But so let's run that and take a look at the mean batting average. Is about 215.
So quickly, let's explain this line of code.
Oh yeah, sure. So what we're looking at here is we're saying in explaining the whole line of code is we have the typical, the way that you call a mean on a vector, right? So we have in the player DF 2018 data set. If we were to just call that, that's exactly what we did above, which is give me the mean of that vector of data. But we wanted to know actually what's the mean of that vector of data conditional on the fact that the player had batted over the median amount. So we put in the square brackets after the vector and we say, you know what? Only find the conditions where the player had an at-bat greater than or equal to, and then I call the quantile function where I want to say the quantile of the player DF 2018 at-bats vector when the probability is 0.5. So when it's the median value, right? That's the 50th percentile, which was 11, which we saw from our quantile at-bats above on line 32 that we had up there. So you can see it's a Boolean, it returns a Boolean value every time the condition is met. And so basically what we're saying is give us the mean of the player DF 2018 batting average every time that the condition equals true. So conditional on the fact that the player batted greater than or equal to 11 times. And we're going to do the exact same thing for standard deviation. It's the same code, just change the SD. So now we have a mean and standard deviation of 215 plus or minus 0.07. And so those are going to be the bits of information that we can use within our James Stein Estimator here going forward. So we'll scroll down, and before we get into the function, we'll talk a little bit about how this is working. The equation right there on line 45 for the James Stein Estimator is z equals y hat minus c times y minus y hat. So let's unpack that a little bit. Y hat is referencing our grand mean. That's the population mean. That's the value that we just calculated above, right there, right? It was 215. Mm-hmm. So that's going to be the population mean. And we're adding that to this little equation that says c times y minus y hat. Okay, well, inside of those parentheses, y is the observed batting average for the individual player that we saw. And we're minusing it from the grand mean. So we're basically taking that observed batting average and we're subtracting out the grand mean, and we're applying this shrinkage factor. So we're multiplying by c. The shrinkage factor is basically telling us how much to regress that player's observed batting average towards the grand mean. And so it's basing this on a few bits of information. It does 1 minus the number of observations. So we're basically saying, well, number of observations minus 3, which is going to be our degrees of freedom. So we're basically the shrinkage factor is conditional on the amount of observed data that we've seen, multiplied by the population standard deviation, so sigma squared. This is the variance of the population, right? We calculated that above at line 39, and it was 0.07. So we're saying multiply the degrees of freedom by the variance in the population, standard deviation squared, and then we're going to divide by the sum of the squared differences. So again, it's the player's observed data minus the grand mean, and then we square those values and we take the sum. So this is how the shrinkage calculation works. And 1 minus the c, 1 minus the shrinkage factor, tells us the percentage that we're basically shrinking the data towards the grand mean. I think in our example here, it comes out to like 0.182 or something like that, or 0.183. So basically 1 minus that is telling us that we're shrinking the player's observed batting average by about 17% towards the grand mean. So if the player's a little bit below the grand mean, they're going to have some reversion up. If the player's above the grand mean, they're going to have some reversion down. So that's how the James Stein Estimator is working here. And let's go ahead and why don't you walk them through how you created this function?
Sure thing.
To do this for us.
Yeah. So we have the James Stein Estimator or algorithm, I guess you could call it, that we're going to be using. And so I wanted to turn that into a function. We've done functions in the past, and so we'll get to that in a second. But one thing that I always suggest people do, no matter what, is document your code very clearly and understandably so that other people can come in and look at your code and understand what you're doing. So we try to do that with our code here for TidyX. And this is going to be no different. But this time I'm introducing an idea, I don't believe I've talked about this yet, called Roxygen comments. So Roxygen comments are a format that you'd use to document your R functions inside of an R package. You don't have to be inside of an R package to be using this, though, because they're just comments. So you can put this anywhere and it's comments, and it just makes it very clear what you're trying to document for you. And so this is a series of special comments that live just before your function that people can go through, and if you're writing a function, you'll be able to pass information to them. For example, the title of my function, so like a generic name for this is the James Stein Estimator. So what am I trying? What this function is the implementation of the James Stein Estimator. What is the description? So I'm calculating the James Stein Estimator for batting averages, and I also included the function or the algorithm that is used to do that. Next, I identify the params or the arguments that go into the function. And so in this case, the two arguments that are going to be going into my function are batting average, which is then I describe what that argument is, so a numeric vector of all players measured batting averages, and param at bats, which is a numeric vector of all players' number of at bats. So it's rather self-explanatory, but this is just being very clear about what we're putting in there. And then I have this at returns. And so this is identifying what am I expecting to be getting out from this. And so I'll be expecting to get a vector of equivalent length of the estimated batting average for the players. So for each player for each batting average and at bats that I put in, I should get an equivalent number of James Stein estimated batting averages out. And so because I formatted it in this way, I could just move this function into an R package that I'm writing, and I can run some functions in there from DevTools, which is the package to help you create packages, and it'll create all the documentation for me. So like when you do question mark mutate, or dplyr mutate, what happened is the folks that wrote dplyr actually wrote very, very nice Roxygen comments inside of the dplyr package, and it reads these Roxygen comments and generates this documentation for us. So I think it's pretty nifty how it does that, and like I said, you don't have to be using an R package to be using these. I think it makes it really clear what you're trying to do, and it just helps explain what's going on. So then we have the function itself that we're going to be using. So we have the function James Stein Est. It takes the function batting average and at bats. First, I do a quick logic check in there to make sure that the length of batting average is the same as the length of at bats, and it will stop if they're not the same, and it'll throw an error going, hey, this equivalency is not true, I'm not running. So this is just to protect you or protect other people from when they're using your function and don't use it correctly. Then we're going to go through and apply what Patrick talked about earlier. So first we want to identify which players were at least in the 50th percentile of at-bats. So we're going to create a Boolean where we take the at-bats vector and identify which locations were at the very least at the 50th percentile or above. And now we have this set of Booleans. We'll then go through and calculate the group mean and standard deviation using that same exact process that we used before, but now we just have it living in this Boolean vector as opposed to calculating it on the fly. We're going to go through and calculate the sum of squares, the player differences from group mean. So this is taking the batting average from the grand mean and subtracting it, squaring it, summing it. Calculate C, which is 1 minus the length of at-bats, minus 3 times the group standard deviation divided by sum of squared diff. So this is just a constant value. And then we finally get to the James Stein estimate, where it's group mean plus C times batting average minus group mean. And then we're returning our estimate. There we go. So now we've got a function where we can feed in any number of vectors or any number of players' batting averages and at-bats, and it'll return to us its estimated batting average for that player, or for all the players that we pass to it.
Yep.
So now we're going to take player DF 2018, which is what we created before, throw it into a mutate. We're going to use our new function, James Stein Estimator, pass in the batting average and at-bats that we have in our data set, and assign that to the field James Stein. We're then going to calculate the standard deviation for James Stein's estimate, where first we're going to do a quick if-else. So if at-bats is 0, we're going to pretend they had 1 at-bat.
It didn't get a hit.
And didn't get a hit. Yeah. Just to like simplify the process. So we're going to take the square root.
Otherwise it'll kick out an inf because you
can't divide by 0.
By 0. Yeah.
So this process is more or less the same. It's just now we're saying that they had 1 at-bat as opposed to however actual number of at-bats they had. So it's going to be James Stein times 1 minus James Stein. Take the square root of that and divide by the total number of at-bats. And that is going to give us the standard deviation. You can multiply this value by n to get n number of standard deviations. So like if you wanted 2 standard deviations, you do 2 times this value to get the broader 95th confidence interval. But we're going to keep it at this one.
Hang on. The at-bats should be inside of the square root. The sample size should be inside the square root as well.
Okay.
I don't know why it's outside. It should be, the square root
live
of P,
debugging.
Yeah, the square root of P times 1 minus P divided by N. So you're going to need a parentheses on the outside of 1 there.
That
shouldn't that be?
Boom.
There's 1
Boom.
parentheses there,
Boom.
yep, and then there.
All right.
And
then this is the closing of the if-else.
And that's the closing of the bracket. Yeah.
There we go. All right.
Okay.
So now we'll run that. And then here now we're going to calculate the low and the high. So the intervals that we would expect the James Stein estimate to be in, because it's just an estimate. And so there's a broad range that the values could be. So this is just calculating the low and the high for us. And if James Stein minus the standard deviation ends up less than 0, obviously you can't have a batting average less than 0, so we're going to set it to be 0. So we're going to run that, and so now we end up here. I'll just run this head here. So now we end up with player ID, games, at bats, hits, batting average, our James Stein estimated value, the James Stein standard deviation, and our low and high estimates for James Stein. That's a lot of information there.
Yep.
But we're gonna add a little bit more, just for happiness, for funsies. We're actually just gonna add the player name here, because right now we only have the player ID. So we're gonna take the player DF 2018 JS, left join. So this is going to keep all the values in player DF 2018 JS and try to add in information from whatever we're left joining. And if it doesn't exist, it'll put an NA in whatever new columns exist from this value here on the right. So we're going to take the Lahman people data set here. We are going to mutate to create a name, which is going to be a pasting of first name and last name, and select only player ID and name, because these are the only fields that we care about at the moment. Because all we're trying to do is add the player's name to our data set. And then join by player ID. And so then we end up with this. So we have player, game, all the information we had before, but now we have the name of the player.
Yay.
There we go. All right, so now we're going to visualize it. Patrick, you want to take us through this?
Yep. So we start by setting the seed because obviously there was, 13,000 players or something like that. So that'll make a very busy plot. So we're going to set the seed so that we can do a sample, just a random sample. And we set the seed so that if you're doing this at home, you can get the same random sample that we got. Of course, if you don't want to set the seed and you just want to rerun this however many times you want, you can get a random 10 players, whatever. So we take our 2018 James Stein data set that we've just finished creating. We're going to filter out, let's just get rid of anybody that had 0 at-bats and 0 batting average. Not because they're not nice people, but because it's not going to make for a fun plot if we pull them. And we're going to just run the quick sample n function right there to say sample n from this data set, just give me a random sample of 10. Obviously, if you're using our seed, it's not going to be random. You're going to generate the same 10 that you're about to see. We're going to throw this into a ggplot where we're going to put the y-axis set to the names of the individual players and the x-axis set to their observed batting average. So what we saw them actually do in the 2018 season. We're going to start with our first layer of this ggplot being the error bar so that the points will sit on top of it rather than behind it. So we set the error bar to be our low and high, our standard deviation on both sides of the estimate, of the James Stein estimate. The width is 0 because we don't want the end pieces, and the size is 5. So we're actually going to make these like big fat lines, and you'll see why in a second. We're going to set the color to gray or light gray, and the alpha, we're going to make it slightly transparent. And then we're going to set 2 points. Point number 1 is going to be the actual observed batting average for the player in that season. And we're just going to set the size of the point to be at bats so that we're just really transparent about the sample size for the individuals that we're looking at. Point number 2 is going to be this blue point, and we're going to set it to the size 5. And we're going to change the shape. So instead of being circular, it's going to be a shape 1, 2, 4, which is this kind of vertical up and down line for each player. And we're going to set that to be the James Stein estimate. So basically what we've done is we've set up these error bars and the James Stein estimate to be what we feel the player's true performance is, and the red dot to be the observed performance based on the number of at-bats. And so the difference between the true and the observed, right, is that the observed performance has some randomness to it. There's going to be some skill and some luck involved with the players getting hits. And obviously the amount of skill and luck is going to be dependent on the sample size of the individual. So the larger the sample that we see, the more confident we are that we're observing that person's true skill. And so we're going to try and account for that within this plot by plotting our James Stein estimates as the straight line with their corresponding error bars. And then this annotate here is just a sort of a hack job way of putting in our own little legend right on the plot itself.
Yeah.
So basically we're telling it, hey, if it's red, it's the observed, and if it's blue, it's the estimate.
Yeah, we picked this actually up from an earlier TidyX. Somebody's submission there. It was super cool. So we've kept it because we think it's really sweet.
So here we see some players. So we can see the guys that have really short error bars are guys with obviously very large sample sizes, so big red dots. And you can see that the blue line for those guys tends to be a little bit low. So basically what it's saying is, okay, there's some skill and luck, and how much we're going to regress them down depends on the observed values. Someone like Taylor Williams, who barely batted, he obviously has a ton of uncertainty. We don't know what to think of that guy at the moment. We probably think that that blue bar right there, which is going to be below average as an MLB batting, as an MLB player, is what we would estimate him to be. Nathan Eovaldi obviously has batted only a small amount. He didn't get a lot of hits. We estimate that he probably has some regression up towards the mean, but even on the high side, he's still probably a below average hitter, which may be why they don't bat him that often. Okay, so that's 2018.
That's 2018. There we go.
So we can chuck this then into 2019. And basically, we're going to get the 2019 data by filtering it out. We're going to do all the same stuff we did at the start. We're going to select
literally all the same.
Literally all the same. Run the James Stein Estimator. This gives us some 2019 estimates, and we're going to interjoin this with the 2018. So basically, the 2018 data here is going to say, well, based on what we saw from 2018 and what we estimate, this is what we believe the player's true performance to be. And so the 2018 in this data set serves as our best guess going forward, as if we haven't played 2019 yet. Best guess of what we think that player is as a hitter. So we joined it all together with our inner join. We put the little suffixes in there, which basically say any column that matches that is not player ID. That's what we're joining on. Any column that matches in the two data sets, just throw in this little underscore 2019 or underscore 2018 based on whether it's the X data frame or the Y data frame.
Shablammy. So there we go. So now you can see we have, it's rather wide. It's 18 columns. But you can see we have these appended to the end there, because before it was just G, A, B, H, batting average, James Stein. Now I have this, so we have an identifier for what?
If we didn't put the suffix in, it would automatically default to X and dot Y.
And that's
which
not
is
really
fine,
useful for us right now.
but it's not very descriptive, yeah.
And so here we're adding this information in.
Yeah.
So now, you want to take us through this one too?
This is the exact same-ish plot. There's a slight difference. So again, we set the seed because we're going to do the same things. We're going to sample out 10 guys. The same ggplot aesthetics. So we have a y-axis and an x-axis, and we have an error bar, all of that stuff.
Yeah.
The points are going to be the red dot is going to be their 2019 batting average, with the size being their at-bats. The blue line, again, is going to be their James Stein. This is going to be their James Stein 2018. So this is their estimate from 2018, looking forward to 2019. And the error bars around that are actually the 2018 estimate. So our goal here is to see if our 2018 estimate is capturing how they perform in 2019. And then in order to give this a little more context, then we can pretend if 2019 was also played, we can throw in another vertical blue bar that shows their actual 2019 estimate based on what was observed. And then we just add an additional annotate for that 2019 estimate blue bar, and we run this. And here we have a cool plot. So there we see Wilson Ramos at the top, and we can see that indeed his 2019 observed batting average, the red dot, is within 2018 his 2018 estimate.
So he's about right. So the blue, the darker blue is our 2019 James Stein estimate.
Yep.
The light blue is our 2018 estimate, and the error bars are based on 2018 as well.
Yeah, that's
so
right.
So we
someone
can
like Michael Franco, the third one down there. Yep. You could see that he actually underperformed what we would have estimated based on his 2018 performance. He underperformed in 2019. Someone like Matt Boyd didn't bat pretty much at all in 2018, so we didn't really know what to think of him, and he didn't bat all that much in 2019, so we still don't know what to think of him. But you could see most of the guys, like Derek Dietrich really underperformed. That's a pretty bad year there for him. Mm-hmm. Kevin Pillar is within his confidence interval based on our estimate.
Mm-hmm.
So
and you
is
can see
Dan.
The James Stein estimators are also pretty close.
Yeah, he's pretty close. Dan Vogelbach is pretty much the exact same player in 2019 that he was in 2018.
Consistency.
Kurt Casale is right inside of his error bar. Almidas Diaz is inside of his error bar. And actually Adam Duvall, if you had signed Adam Duvall or had him on your fantasy team, you're probably excited because he outperformed what we would have estimated. So he actually improved and got better. And we expect this kind of thing because it's essentially a very simple estimator. It's not accounting for things like aging effect or changing team or park effects. You can go through and count for all those things. This is a very, it's a dumb estimator. It's a simple estimator. So
it's just looking at all the data it has and goes, I don't know.
Yeah.
Well, not
It's
even
a
looking.
pretty cool and simple way to do that, and we could, which you should probably do. Maybe we should have, but you could calculate like your mean squared error or your mean absolute error, and you could estimate, how off were we, and those kinds of things.
How do we alter that?
Yeah,
we should do that. If you, how good are our fits?
Yeah, we could do
Fit
that.
evaluation. Yeah.
I mean, we have both we have the 2018 James Stein and the observed 2019. You could just do mean of one minus the other squared.
This would be
Or maybe do mean, do absolute. So do mean.
2019. We want the 20. So batting average of 2019 minus
The
player
James Stein, DF.
player DF.
Yeah.
2019 James Stein of 2019 or 18 though.
2018. Yeah. So if you did actually get rid of the mean there first, get rid of the absolute too, and put hist. Like, let's just see first, like how.
Not gist.
Or gist.
It's the gist of it.
Let's see what the histogram looks like. So how.
Did I put an extra? Yeah.
There you go.
There we go.
So, and we haven't filtered out anybody who didn't bat or who batted 0 times, obviously. But you could see there, our histogram, it has a massive amount of kurtosis aligned right along 1. So those are the differences. And then we can do the mean absolute difference to get a sense for
that.
Whoop. Uh-oh.
Yeah, we're good. We didn't crash.
Yeah, no. Issues with our studio.
Yeah.
Okay, so the mean absolute difference is about 0.07. Average of about 0.07. On average, that's the...
and the mean squared
on average,
error.
That's the error we're making. Yeah.
So,
0.2, and then you can also do the square root of the mean squared error, so the root mean squared error. And these are all, so we're making an error of about 0.13 plus or minus. So those are different ways that you could evaluate your estimates, and then you can figure out other things to account for. Like, for example, maybe subsetting everybody that at-batted over the median, the 11 at-bats. Maybe that was,
too low.
Maybe that's not conservative enough, or it's too low. Exact.
Yes.
Different ways, but let's have the big crescendo here. Now, evaluated our estimates. Let's have a big crescendo and chuck this all into a cool visual with AT.
Exactly. So now we're going to make a GT plot, and I wanted to make this also reproducible and allow you to do what you wanted to do. So you can alter this as you want. So we're going to take the player DF. I'm going to filter to keep out any players that didn't bat in 2018 or 2019 or had a batting average of 0 in 2018 or 2019. Because once again, not to comment on them, it was just less interesting visualization. And then we're going to sample 10 of them. So then we end up with these 10 different players here. And then we're going to create the viz data frame for us. And this is what we're going to use for the rest of our visualization. So we're going to take the player DF 2019. We're going to filter to keep only the cases where player ID is one of those 10 players we identified, and arrange it by player. So that way we can keep the order the same. And then just to make sure we preserve it for all the various pieces, we're going to convert it into a factor and set the level to be the name. So that way the order in which they show up in this data set is going to be the order in which they get plotted. So then we have viz data here. So then we've got these 10 players and a bunch of data about them. And we're going to make a table for them first. So we're going to take viz data. We're going to actually flip the order because I know later on when I do plotting, it orders from bottom to top, not top to bottom.
Yeah.
It's an interesting quirk of ggplot. Then we're going to select. We only care about some specific columns. So we select name, games from 2018-2019, bats from 2018-2019, batting average from 2018-2019, and James Stein from 2018-2019. This can be a little annoying to edit. So what you can do if you're working in RStudio, you can press Command or Alt, and you can actually click and work across multiple lines. So that's how I was able to edit these rather quickly, is I put 2018, 2019 and just kind of tabbed through all of them and edited them that way. I threw it into a GT, and I set the row name call to be named because I don't really care about setting it to be a column, and I want to present their names there. I'm going to give them pretty labels, but in this case, I'm only wanting to keep the year that they had. So games 2018, 2019, I only care about keeping 2018, 2019. Same for at-bats, batting average, and James Stein. And this will show up in a second here because I'm going to do tab spanners. So these are going to have a little header across the two columns at the top there and give a generic label at the top. So this is going to add a tab spanner for the label, or set the label to be BR games, so it's HTML, because there are going to be table spanners later on that cover two rows, and so having this BR at the front there sets games to be just have a new row, new line, and then games. And I'm going to set it for all the columns that start with G. So the only ones that start with G are G 2018 and 2019. Same idea for tab spanner for at-bats. So I'm going to have a new line for at-bats, and any columns that start with AB will have that as the table spanner. Now for batting average, I'm going to give it a prettier name, batting, line break, average. And it's going to span across all the columns that are batting average. Same for James Stein, batting average. I put a BR between James Stein and batting average, and span across all the columns of James Stein. I'm going to number all the columns that have decimal places, which in this case are batting average and James Stein. And I'm going to set the decimals to be 3 because I don't really care to show more decimals after that. And I'm going to add some styling to some cells here. So tab style, so table style. I'm going to set the style. The cell text is going to be red. And the location this is going to happen in the cell's body, it's going to be columns that start with batting average. So all the batting average columns are going to then have red text. Same idea here, except James Stein columns are going to be blue. Sorry, so that's kind of a lot of styling. GT has a lot of minutia details that you can select, but really what we end up with is a table that looks like this, where we have rows for each player. We have spanners across the multiple years. I thought it was useful to compare year to year, each different stat, as opposed to grouping year 2018 and year 2019. That way you can look across immediately and go, Michael Taylor in 2018, batting average of 227, and 2019, 250. And in 2018, their James Stein batting average was 225, so James Stein brought him down a little bit. And same in 2019. So Michael Taylor might be an above average hitter, at least based on what we're doing here. And then you can look at the number of games they batted in. So like James Taylor in 2018 had 134 games, and in 2019 only had 53. So that also could lead to some of the variance there.
Yeah, and he was regressed more in 2019.
Yes.
Than he was in 2018.
Exactly. Here we're going to do a plot of the 2018 data, very similar to what we did before. Take the viz data, y-axis is going to be name, x-axis is going to be batting average for 2018. We're going to have the same error bars, points. We're going to have the same vertical line for the James Stein Estimator. I'm setting the limits to be between 0 and 0.45 so that it's consistent across multiple plots. Setting the label to be title of 2018 batting average, and setting a little bit of theming. This case, I don't really care to keep the y-axis title because it's names that we're providing, so there's not much context that's necessary for that. And I'm removing the y or the x-axis title as well because I have that in the name of the actual plot, and I don't really care to have a legend in this case for this plot. So let's take a quick look. So this is the 2018 plot. I'm going to do the same thing for 2019, except using 2019 values. And I'm also just going to remove the ticks for the y-axis as well because it's not useful, and you'll see why in a second. So now I removed the
Just making sure that the same names are on the same.
Yeah, there's no real value in keeping that.
That's right.
And so now I'm going to convert everything. I'm going to put the table and these two plots next to each other using Patchwork. And this was actually inspired by Thomas Mock, the guy that founded Tidy Tuesday. He posted this gist. Somebody asked how you could use GT tables with Patchwork. He's like, oh, here's how you do it.
Yeah.
So we're going to go over it really quick.
We had an interview with him in episode 10, maybe? 12, there you go.
12.
Okay.
Yeah, so definitely check that out. I'll provide a link. But yeah, so we're going to take going to create a temporary file here so that it doesn't get saved in your directory when you run it. I'm going to set the extension to be a PNG, and this is important because when I go to save this table, GT save looks at the extension to figure out how to actually save it. It does some magic in the background. So now I'm going to save a PNG of the table that we had. I'm then going to read it back in, but now I'm going to read it back in as an image so that I can add it into Patchwork. And so I'm going to use magic image read, the path to that temp file that I had, and then I'm going to convert it into a ggplot object. So it's kind of going round trip.
This is literally magic.
Literally magic. And so this is the table. Ooh, that looks not great. But yeah, this is the table that we just looked at, but now it's been converted into a PNG for us. So that looks pretty nice there. But now we're going to combine it with Patchwork. So we're going to take GT image, plot from 2018, and plot from 2019. I'm going to set the layout to have 3 columns. The width of the first column is going to be half of the plot, and then the next or half of the generated image, and then the next 2 plots are going to be 1/4 apiece. If there were guides, it'd collect them all. So this would like be a legend. It would collect them all and put them on the right-hand side. And then some plot annotation. So the title, James Stein Estimates. Subtitle, 2018 and 2019, batting averages. Caption, plot from Tidy Explained. Data from Lahman. Theme, now I'm centering the plot title in the plot subtitle to H just of 0.5. So this is going to center them in the image that gets generated. So let's just zoom because it's going to look like garbage in that viewer anyway. But awesome. Here we go. So now we have all this information compiled into a single location. So we've got information, this table here where we have information about games and at-bats for all the players here. And then we have batting averages for 2018 and 2019 and our James Stein estimates surrounding there. So it's just, I think, a fun way to visualize all this information.
Yeah.
All combined.
Fun with estimates.
Fun with estimates. All right. So let us know what you think. Thank you once again for being with us for 50 episodes. Ooh. This has been a fun ride for us, and I'm looking forward to I'm looking forward to the future and hearing from y'all. So with that, let's call it. My name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSP Patrick, and you can hit us up on Twitter for the screencast at tidy_explained, or ping us an email, tidy.explained@gmail.com, or drop a comment on the YouTube video and let us know what you think.
All right. Thank you so much, and keep on exploring your world.